Good morning. It's a pleasure today to receive Rick Willemsen from the Erasmus University, Rotterdam. Rick is here for his PhD stage. We spent very good, very fruitful 3 months that open research venues for future collaborations. Today, in fact, Rick will present a work which is not related to what we have been doing, but it was an important part of his PhD, let's say, trajectory. He participated in the ROADEF challenge in 2022. The ROADEF challenge is organized by the French Operations Research Society. And Ricky and his colleague from Rotterdam too, Bart, they were awarded with the first prize in the junior category. And this is the main topic, in fact, of his presentation today. So, Ricky, thank you for your seminar. And please.
Thank you for the introduction. Yeah, so you kind of covered my introduction already. But indeed, so this project that I will be presenting here, it's not part of our PhD project. So it's really separate from the research that we're doing ourselves. So I actually want to start off with some pictures that I have here. Because so this whole process of working on this competition, it took almost a year. And part of this time, Bart was actually in New York for his research visit. And so we had to work on the project while having this time difference. But luckily, we both went to Montreal together to a column generation workshop here. And so during this conference, we actually got quite some inspiration, and we also worked on the project during the conference. So that's why there's we got some inspiration here. And then we got the certificate actually this week, finally. And that's which shows that we got the first prize in the junior category. So, yeah, so this competition, it's organized by the French Operations Research Society every 2 years. And one of the main reasons is because you will see later, it's quite a long schedule. So we almost spend the whole year on it. And they often collaborate with industrial partners. So in this case, that was Renault, the car company. And so this Renault provides the data. And then they basically give it to us and then expect us to solve their problem. And then there's basically 2 streams. So there's the junior category and the senior one. And the junior is for the people who did not defend their PhD yet. And so that's where we participated in. So this is an overview of the timeline. So it started in 2022 in the summer. And it's basically divided into 3 different rounds. So there was a sprint round, a qualification round, and the final round. And it actually finished in the summer. And after that, there are still some paper submission that you could participate with. And of course, the most important one was the one from July 13, in which we got the results. And then, of course, one of the main motivations to participate, there's a monetary incentive. So at each of the rounds, there was some award that you could win. And then so we got this one over here. So what is the problem that we have to solve? So Renault, it's, as you know, quite big, but just to give you a sense of the scale, their supply chain covers around 17 countries, and they need to supply their 40 plants using around 1,500 suppliers. And every week they have to make this schedule for the truck drivers of where to which supplier to go, and then to which plant to go, and then which items do you have to take with you. So for this specific problem, the routes of the truck are already fixed. So we know that, for example, truck 1 will first visit supplier A, then supplier C, and then visit the plant, for instance. And we just have to decide which item do we assign to which truck, and how can we arrange these items in the truck. So that's visualized over here. So basically we have items, and we combine multiple items into what we call a stack. So the stack contains maybe 4 or 5 items in some cases. But there are some restrictions. So not every item can be on top of another item. So for instance, maybe item A can be on top of B, but not the other way around. And there's also restrictions that not every stack can be assigned to any truck. And the trucks are also heterogeneous, so some may be a bit bigger, but they also cost more money. And then so there's two goals. First of all, we want to minimize transportation cost. And this is purely determined by the amount of trucks or which trucks we use. And actually, so they already have the fixed routes, but we can say, okay, we choose this route 5 times and the other route 0 times, but you have to pay a penalty for choosing a route multiple times. So if you just look at the transportation cost, you might think, okay, we want to assign as many items as possible to the trucks in order to minimize the number of trucks. But if an item arrives before it's needed at a plant, then they have to store it somewhere at a plant, which is quite costly for them. So if your item arrives 1 day earlier or 2 days earlier, it will incur a penalty cost, which are the inventory costs. So in order to minimize inventory costs, you basically want to have that all the items arrive exactly on the day that you need them. So you see that there's some balance that has to be made. So you don't want to have too many trucks, but also not too much inventory cost.
Yes. When you say fixed route, so each truck has an already prefixed route or a set of routes?
I mean, so they give all the routes already. So it could be that the same truck has multiple routes, but we don't really take that into account. We just look at the whole route, if you understand what I mean. So it could be that there's 2 routes with the same truck characteristics. So with the same costs and with the same dimensions. And so I will now briefly talk about all the constraints, and there are a lot of constraints that we have to satisfy. We divided into 4 different levels. On the item level, on the stack level, which has multiple items, the placement, which contains a lot of stacks, and then there's the weight balance constraint, which just deserves its own category because it's, as you will see, quite a difficult one to take care of. So what you see over here is the side view and the top view of the truck. So each of these, on the top view, you see the stacks. And the stack consists, for instance, of A1, A2, and A3. These are the items. And maybe it's already important to notice, but all the items or all the stacks are pushed as much to the front as possible. And the reason for that is as soon as the truck brakes, they don't want any of the items to move to the front anymore. So for example, we see that stack Y is allowed here because it connects here with the with stack X, so it cannot move to the front. So this is feasible stack placement. The items should be compatible with the truck. So not every item can be assigned to a specific truck. And you also have to make sure that it's picked up at the correct supplier, it goes to the correct plant, and that it arrives within the time window of the item. Actually, most of these constraints you can take care of during the pre-processing phase. So mostly you only have to take the time window into account to calculate the inventory cost. Then about the stack constraints. So here you see an example of the stack, so AA1 up to AA3. All the items in the same stack should have the same supplier and the same plant. And they should have the same dimensions. So what I mean is that, so the width and so everything should match except the height of the item. Other than that, there's also a maximum density. So there's not to be allowed too much weight on a specific square area.
In the second picture, what are those gray boxes on the left side of the wire?
Oh, these.
Yeah.
So they want to make it as realistic as possible. So we only see the first row over here. So the gray part is the back row, basically.
Nice.
Yeah, I just copy pasted these pictures from their information. And then so there's a maximum weight constraint. So it says that the bottommost item is not allowed to have too much weight on top of it. And then there's also a maximum number of items. Then about the placement. So as I mentioned before, we have a truck which starts empty, then it visits multiple suppliers before going to the plant. But this means that when you load the truck at the first supplier, you have to make sure that you fill it up, for example, up to the red part, such that all the blue items from the second supplier can easily be loaded in as well. So this is something you already have to take into account when planning the truck. So on the picture here, you see only the supplier order, so the red and the blue part. But within the supplier, you also have other types of orders. In total, there's 3 nested orders that we have to take into account. So in some sense, you could say that this restriction makes the problem a bit easier, because most of the order becomes already fixed. So, you know, this item will never be in front of the other item. And finally, there's the weight constraint, which is the most difficult one that we had to take into account. It's quite easy to calculate as soon as you have a filled truck. It basically says that the front and the back of the truck are not allowed to be unbalanced, basically. So there's not allowed to be too much weight on the front or too much weight on the back. But what makes this really difficult is that it should hold whenever the truck is on the road. So basically, between each supplier, the truck should be balanced. So you can imagine in the morning it starts empty, so it's by definition balanced. But then it first visits the red supplier. And as soon as all the red items are in there, it should be balanced while it goes to the blue supplier. And you might think, okay, assume that we put 1 stack each time in the truck, and you could calculate if it's balanced or not. But this, unfortunately, it would work, but it's not efficient. So it could be that, for example, if you only put stack A, stack C, and stack E in the truck, it could be that this truck becomes unbalanced, even though if you would fill it up with all the red items, it's balanced again. So this makes it really difficult if you're trying to put items in the truck.
And so, just because it's the weight, you also have a weight distribution on the left and right side.
No, it's only the front and the back. So otherwise it would be even more complicated. Yeah. But so actually one thing you might, so I think it's not really a problem, because as you can see, you can always move these items a little bit to the side. I'm not sure if that's what they do in practice.
Because I did a similar project, and the company had also the left and right.
Yeah, I can imagine it makes it even more difficult. So, yeah, so we were just looking first in the literature, like what has been done before. And there's like almost any type of heuristic that you can think of has been used for these types of problems. But we noticed that common generation wasn't really used a lot. We could actually only identify 2 papers that used a common generation approach for this type of problem. But maybe correct me if I'm wrong if you know other papers. So the first one that we found was quite a standard column generation approach. I will talk about column generation later as well. And the second one used a bit more complicated one, in which they call it a prototype column generation approach. They first solve the pricing problem, where they remove a lot of the constraints. So you basically get infeasible trucks, and you add them to your column, to your master problem. And as soon as you have that, you try to replace these prototypes with feasible trucks again. That's the only 2 papers we could identify. And here we have a short overview of the types of characteristics that they considered. So for example, for the objective, we see that the paper from Malvash, they only considered the number, to minimize the number of trucks. And then the paper from Chu and others, and in the ROADEF challenge, we have to minimize costs. Then the paper from 2017, they had homogeneous trucks. So all the trucks have the same dimensions. It's also the same cost. Maybe interesting to see is that, so we have what they call guillotine constraints in the literature. So these are basically the stacks that we have. So you're only allowed to place an item on top of another item if they have the same dimension. We sometimes allow vertical rotation, so that just means you rotate it like this, and not, you can't put the item on top of, like you can't put it upside down. But we have these extra constraints over here, order constraints. So I'm not really sure if this makes the problem easier or complicated, but the balance constraint will definitely make it more complicated. And I think this is the first time that it's used in a column generation procedure. And so what I will talk about the rest of the presentation is about this column generation and how we solve the pricing problem. So here's a short overview of how our methodology looks like. The first three boxes, they're basically our start heuristic, because we want to find a good solution as fast as possible. So we have two different ways. There's a greedy heuristic. So that one just finds a feasible solution immediately. And on the right, we have a two-step procedure. We first solve a mixed integer program in which we remove a lot of constraints as well. This gives us an infeasible plan. And then we try to turn this infeasible plan into a feasible one again. But so the nice thing about this second procedure is that we also obtain lower bound information. So we have some indication of how good of a kind of what's the lower bound on the costs that we could obtain. Then using all these feasible solutions, we initialize our column generation approach. We solve it, and then we always apply a post-processing algorithm, because we always notice that there's some possibility to improve. It's every time we finish the column generation, there is still some improvement possible. And then in the remainder of the time, because there's a time limit for the competition, we just keep doing this last loop in which we start with the best solution found till now, and then we remove part of the solution, which we think basically the worst trucks, and then we solve the column generation again. So for the ones who are not too familiar with what column generation is, basically we have a lot of columns, and each of these columns correspond to a truck. For example, the first truck covers item number 1 once. The second truck covers item 1 5 times. And on the right-hand side, you see we have to cover it in total 9 times. And we have decision variables which are binary, which decides, okay, do we select the truck or not? So if you would give this to a solver, it will just give you a global optimal solution in which you'll find the best solution. Unfortunately, that's only possible if you can write down all the possible trucks, and there's just too many of these. So therefore, we use what we call column generation. We just generate the trucks of which we think will contribute to finding the best solution. And these trucks are found by solving what we call the pricing problem. So the pricing problem says, oh, you should add this truck. We add it, and then we solve the pricing problem.
But where is the layout of the truck? I mean,
yeah, so the layout is stored in there as well. But as soon as we made the truck, we know this is a feasible truck. And then we don't care anymore about how it looks like, so we don't have to store that in. So we knew it was feasible, and then we just give it to the master form. So we think this approach has some advantages, because we are solving, let's say, a global assignment problem. So we're really saying we want to choose these trucks and this truck, which covers all the items. And at the front, I already mentioned we can generate a lot of feasible solutions. The pricing problem, which will come later, it's quite an intuitive way of how you would pack a truck yourself. And we have a lot of parameters. And actually, so we do obtain lower bound information. So we did it from the start heuristic. And also, if you solve this column generation procedure, you obtain some lower bounds. The only downside is, because of the time limits, the lower bounds might not always be reliable enough. So this are we covered. So for the assignment model, it's quite basic. We just say we have decision variables in which we say how many items do we assign to a truck, and which trucks, and how often we choose a type of truck. And we only take the weight and the volume into account of the items. So we just check if we sum up all the weights of these items, does it fit into the truck or not? So this as you can see, then forms a lower bound for the optimal solution. And after we found this lower bound, we have to make a feasible truck placement which covers all which satisfies all of the constraints. We actually do this in parallel using multi-threading. So we do it 8 times at the same time. So we get really a lot of different solutions. Then this is for the greedy heuristic, also to get the start solution. So here we noticed something interesting when we looked at a lot of solutions, which was that, so the transportation costs, there seem to be more important than the inventory cost, in the sense that, so suppose you have a truck which only contains a few items, then you would rather discard the truck and then give the items to another truck which should arrive later, for instance. But you don't want to arrive more than 1 day too early. So that's kind of what we do over here. So we just assign all the trucks to the same date, and with some probability we assign it 1 day earlier. And we noticed that these solutions were already quite good. And then in the second phase, we just try to combine multiple trucks together. So now we go into the column generation. So actually, one of the downsides of column generation is that, as you saw earlier, we want to satisfy that we have, for example, at least 9 items of the first type. But so at some point we have to branch. So for example, we say, okay, we want to have this truck or not. But if as soon as we choose a specific truck, it might happen that we would cover too many items. So this is actually a real problem because, for example, because of the weight balance constraint or because of the order constraint, as soon as you remove this item again from the truck and you want to leave the truck the same, the truck might become infeasible. So in other words, overcoverage is not allowed when branching, when doing the dive and fix procedure. So whenever we fix one truck, we have to remove all other trucks that become infeasible. I hope that is clear. Yes, and then also what is really important here is we have, at some point we will see we have maybe 6,000 different truck types. And for each truck type, we have a lot of different columns. So it's really important to do column management here, because otherwise the problem just grows too big to solve.
So trucks have all the same dimensions, or you have different types of?
Yeah, so for instance, we might have, let's say, 5,000 truck types. And each truck type could be selected, for instance, once or twice or 3 times or 0.
By truck type, you mean?
So that's the fixed routes with a specific dimension.
But like the area inside the truck is all the same, the volume?
No, that can also differ per truck, and then the cost will also differ. And so at the end, when we have too much time left, for instance, we just keep doing this loop in which we unfix some of the trucks, which we think are the worst, and then we fix them, and then we solve the column generation procedure again. And we're actually quite aggressive here. And that's just because if you're not aggressive enough, you might not find enough solutions. So this is what we call the intuitive way of packing a truck. So we know already that supplier A must be before supplier B. So that's over here. And then what we do is we first sort the items based on what we call negative reduced cost. And this basically gives an indication of how well it contributes to the objective. So we prefer like to have item A1 and A2 over A6. What we then do is, so we know that these first 2 might have the best negative reduced cost. But it could be that as soon as you place A1, it might be that A2 is not allowed on top of A1. So it can still happen that the order changes when creating the stacks. And because of this, it might be that if A6 and A6 has a really bad net reduced cost, then this stack might be not that useful anymore. So that's why in the second step, we sort the stacks again based on negative reduced cost. And so we do this per supplier. And so you can imagine that every time we solve the pricing problem, so in each iteration, these stacks will be totally different. So that's why we kind of call it dynamic pricing problem. And in this way, we try to explore as many different trucks as possible. As soon as we have all these stacks, so they're now on top, we put them in this directed acyclic graph. And the goal is that we want to start at the source node, and we want to finish at a sink. And we want to find a path through this network, which has in total the most negative reduced cost. And this is, again, a really difficult problem to solve. So what we do is we perform a labeling procedure. So we start at the source node that has 0 cost, basically. And then you extend it to all the possible outgoing arcs. So you go to A1, you create a new label, go to A2, you create a new label, and you also go to the end node, which creates a new label. And then basically, then we select the next label, which has the best reduced cost. And then we do the same procedure until we reach the sink. So this is how one of the labels looks like. It's basically already a truck. So this is the front of the truck. And at the moment, it contains 3 stacks. We actually make sure that each label is feasible with respect to all constraints, except the weight balance, which we will check later on. So as soon as we want to extend the label, so when we go from one node to the next, we consider what they call corner points in the literature. There's also other versions, but we found that this one worked the best. And actually, we just select every point, which is the most left, most to the right. So these are denoted in black. And we also select this as a corner point. And then what we do is we just try out the most left option, the most left corner point. If it fits, we just put it there, and then that's our label. If it doesn't, then we try out the next most left corner point, and we continue like this. And the reason for this is because of the supplier order. So we want to make sure that all items from the same supplier are at most to the left as possible. So this is it's quite a standard labeling algorithm.
Yeah, sorry, just a quick question. Can you put that in? So do you allow like this overhanding unlimited? That's on the top item is going, it doesn't have support. Right?
But this is the front of the truck.
Okay, so we're working from up.
This is the up view.
Okay,
I'm sorry. Yeah, so these are all stacks. So we have now 4 stacks, and you just have to make sure that you can't push them anymore to the left.
Yes, just to see if I understand correctly. This is what you're doing is generating columns that are generated according to some heuristic of how to practice things, but it doesn't go to necessarily all the possible ways.
Yeah, exactly. So that's kind of what I was. So, okay, imagine that. Yeah, so for instance, if you want to find, let's say, the optimal solution to this pricing problem, you would have to generate all possible combinations of stacks.
And all possible ways.
Yeah, and then you need to go through this whole network and find all possible paths. So that just it's just too big for even a single truck. So the main reason that we do this approach is that at each iteration, every time we call the pricing problem, these stacks will be different. And then so in that sense, we hope that we can still cover a wide area of different stacks. So if you have a lot of different stacks, then hopefully you will find good columns. That was the main reason we do this.
And for everything you tested, your hope was confirmed. I mean, for the instance that were provided by the channel.
Yeah, I will show some computational results later, but I mean, there's no way to. We actually don't know if this was the bottleneck or not. Because there's just no way to compute the optimal solution to this, or even some nice lower bounds. So we have no idea how good this pricing problem is working.
Yeah, you know, because you went first.
For the 3 years, right? Yeah. Yeah, but I mean, it could be that this is working extremely well, but the master problem is just way too big. So that it's just something we don't know what the real bottleneck was. But for example, what I will show over here is we're really aggressive when going through the network. The network is actually huge. It can easily contain like 40 stacks. And so the final solution contains 40 stacks, but you could choose out of many more stacks. But we only keep track of 25 labels at the same time, at any point while going through the graph. So that's really a small number, actually. And in the end, we give 5 trucks, 5 columns back to the master problem. And as I mentioned before, we make sure that all constraints are feasible, except the weight balance constraint, which will come now. So basically what we do is we just reach the end of each supplier node. So at each of these, what we call supplier nodes, and at a sink, there, at that point, we check if the weight balance constraint is satisfied or not, because it should be satisfied at each supplier node. If it is satisfied, then we're done already, and we don't have to change anything. If it's not satisfied, for example, if we only selected A1 and A2 and it's not feasible, what we do is we start from scratch again, but we still want to assign the same stacks in the same order. So originally we would put this item over here, this stack over here. But maybe this would be better to make sure that the truck is balanced. Yeah? So how do we do that? We actually try to use a lot of things from the literature, or like some rules, like, okay, if you have this much space left, you should put it there. But it all didn't work. What we did in the end is, with some probability, you put it here. With some probability, you put it here. So it's really random, but it worked really well. And because of this probability, on expectation, you want that this part is empty, the top part. And that seemed to work well in practice for us. So now about the post-processing. So this is the last phase that we always execute before giving the solution. We have 2 procedures. One is what we call combined trucks, and the other is remove trucks, but they're based on the same principle, which is visualized over here. So we have 2 trucks on the left. And we see that because these are rotated in a different way, it is not possible to fit all 4 items in one truck. But if we would have a specific rotation, all items would fit in the same truck, and then we can save cost by removing this one. And the combined trucks is based on, so we noticed in a lot of solutions, there exists a solution in which items from, so suppose we have 2 trucks from the same type, and one of the trucks has, for example, 1 or 2 stacks, and the other one is full because we had the wrong rotation. But we noticed that there always existed a solution, if you have the correct rotation, that it would fit in a single truck. So that's kind of what we do in the first one. We kind of try to keep rotating the stacks until you find a solution in which you can remove the second truck. And so we think that's also how they generated the data. Because so they use this in practice, so they probably have a lot of data in which I don't think they will actually like transport 1 stack in a single truck. So the data they provided should also probably not have this. So we just kind of try to enumerate until we find this solution.
After you rotate any of the items over there, do you go back to the weight constraints to check the weights again?
Yeah, so, okay, yeah, that's indeed something that I should mention. Yeah, basically, so this is what we call the pricing problem, but we use it for any other heuristic as well. So we use this for the construction heuristic, so to give the start solution. We use it for the post-processing when combining trucks. So we use the same framework every time, except that, for example, for the combined trucks, the stacks are already fixed. So the order of them is already fixed. So only in the pricing problem we do sorting. Okay. And all the other ones, the order always stays the same. Yeah, and so for remove trucks, it's the same idea. But there we do it not just for a single truck type, but for any other truck. So, for example, we have this one, maybe there's 1 or 2 items left. And we try to assign these 1 or 2 items to any other truck and it doesn't have to be from the same type, or the stacks also don't have to be together anymore. Oh, and maybe it's also good to mention, for the combined trucks, we also did it on the item level. Whereas for this one, we only do it on the stack level. So let me first show you a bit about how big these instances are. So the time horizon is normally you have to plan for 10 or 15 weeks in advance. I will discuss mostly the small and the large instances. So the largest one here are like around 30,000 items, and you can choose around almost 4,000 different truck types on average. But in the end, for the final results, our algorithm was also run on instances with 50,000 items and 6,000 trucks. But I will mostly discuss it first. And just to give you an idea, so every time we have to decide which trucks do we want, we fix 10 trucks at least at the same time. And the reason for this is if you would only fix a single truck, you might need like 6,000 iterations before finding a solution. So we really want to speed up finding the solutions. And every time we have found the best solution, we unfix the worst trucks. So we look at if they're not filled. So we look at the weight and the volume. And we also always select some random trucks, around 25% of the solution, which is quite big actually. So it could be that here we remove some really good trucks, but we don't remove them from the entire model, so we can always select them in the next round again if they are indeed so good.
Do you have a time limit for?
Yeah, so for most instances, there was a time limit of 60 minutes. For some, there was 30 minutes. So it differs per instance as well. So you just have to return a solution within 60 minutes. So these were the final results. So we're actually the 5th place, but we are the first juniors.
By far, actually, the 2. I am 9th place.
Yeah, 9th and 13th. And so we were evaluated on 50 known instances and 105 instances that we never saw before. And it turned out that these hidden instances were actually really huge in some cases. I'll talk about it later. So I first wanted to show you what do we spend the most computation time on, and this is in minutes. So for the small one, we see the assignment model and the construction. So this is where we find the initial few solutions. On average, we spend like maybe 4 minutes on those. So within 4 minutes out of 30 or out of 60, we already have a decent solution, I would say. Then we spend some time on finding this root node. And then we spend a lot of time on this loop in which we unfix the solution, fix it again, unfix it, etc. And then the post-processing is really fast because it's just too easy procedure. Unfortunately, it turned out that if you really scale off the problems, our method might not be really scalable. So we see that as soon as we go to the somewhat larger instances, we spend a lot more time on the root node. And this is quite something that is known in column generation, that for some problems, it's really hard to converge. And that's what we see over here. It just took way too much time to find a decent solution. And so we also had to put a time limit on solving the root node, otherwise it would cost too much time already. And so we see we also have less time to do the resolve, so doing multiple loops. These are the gaps with respect to the best known solution, so out of all the other teams. So we see that on average for the construction, so our start solutions are on average 20% off from the best known solution. And we feed all of these into the column generation, and we see that after the first iteration of column generation, we shave off like 10% gap, which is quite good, I would say. And then the resolve does improve, but it's really difficult. So it does feel like we are stuck in a local optimal solution. And so these are the results on the evaluation instances. So these are the 150 instances of the final round. And we again see the gap with respect to the best known solution of all the other teams. And I sorted these instances based on the number of items. So I think it becomes now really clear that color generation is not scalable for these types of problems. Because when we started the competition, they mostly gave the extremely small instances, and we were actually quite competitive there. But then in the final 2 rounds, they suddenly gave these really huge instances, and we couldn't really adjust our methods too much anymore. And actually also interesting, so we ran the same instances on our computer server, and they ran without a problem. But actually, when running it on their server, we did end up with some errors. And that was because we solved this assignment model at the beginning, but we imposed a time limit. And whenever we solved it, we could always find at least one solution within the time limit. But it turned out that their computer is a bit slower, so we did not account for that. So we ended up with, after 5 minutes, we just timed out, and we didn't have a solution to give to the column generation. So we just never considered that option. So during the process, so I now just want to finish up with how the process went and maybe some takeaway messages. So we had a lot of ups and downs. So a lot of there were so many bugs to solve, and it was not always our fault. So sometimes it was on the fault of Renault or the competition organizers that they provided the wrong data, or that their checker was not feasible. And we actually have quite a long list of things that we would have liked to know before we started. There's some positive things at the end. But one of the things we noticed that, I mean, it makes sense, but collaboration is really key. So sometimes we were both programming, but you make some minor assumptions so when you program on your own, you just know that it should always be like this. But if you don't tell each other, this might lead to some really major problems, and then you just get bugs again. We also noticed that you should not change any codes like a week before the deadline. We did not learn from this mistake in any of the rounds. So it was really stressful. Each of the 3 rounds were actually quite stressful for us. And on top of that, in the final rounds, actually the university was migrating their computer server. So we also did not have access to the computer server in the final week while we were still finding the bugs. So I would not recommend doing that. Yeah, so this I kind of covered before. So even if your code works on your own machine, you really still should actually think about, is there any way if it's runs slower on the other computer, can anything go wrong? So that's something we did not consider. And also about these deadlines. So there's 3 deadlines, which is quite a lot, I would say, for a competition. But it also meant that after each deadline, you really had to improve your method. Otherwise, you would just be behind again. And we also had this sunk cost. So we noticed at some point in the second round, basically, that our method was not scalable enough. But we were already so invested that we did not want to change anymore. And on the positive side, we did learn a lot as well. So for instance, I explained about these random things that we did. We don't have to support why we did it. And whereas while you're writing a paper for your own research, you always have to motivate certain choices. So I think that's quite nice of the competition. We also learned a lot. So I mentioned this multi-threading at the beginning. We both didn't use it before. So it was quite interesting to finally use that in practice. And we have some final discussion points. So first of all, this competition was really tailored to Renault, and I think they will benefit the most of it. And actually, so they award what we think is maybe quite a lot of money, like around 30,000. But for them, it's really not much, and they get a lot of research ideas back for it. What we did find interesting is that this is actually a nice way to benchmark multiple methods from the literature with each other, because you can't cherry pick the instances. It's all run on the same computer from them. Because, for example, what we noticed.
But the programming language could be different.
They can be different indeed. Yeah. But for example, what we noticed is we did try to implement some things from the literature. So I talked briefly about the corner points, and we tried some different strategies. But a lot of them didn't work for us. So it could be maybe that the whole color generation is maybe not suitable, or these ideas really don't work that well in practice. And finally, we should support PhDs to also participate in this. At least this was our opinion at our own department. So I'm not sure if it's any different here in Europe. So thank you for your attention.